I had some technical difficulties with this video, so I'll be doing some just revealing things, but a lot of it I'm just going to work all over again. So, direction fields and Eulers method. These are for when you can't actually solve the differential equation, but you would like to see what solutions look like, or you want a good estimate of what a solution to an initial value problem would be. So our goals for this section: to determine, be able to sketch a solution through a given point on a slope field, determine the slope field that represents a given differential equation. Notice I didn't say that one of our goals was to be able to draw a slope field from scratch. I won't expect you to do that. And to use Euler's method to estimate the solution to an initial value problem. So, direction fields. Like I said, unfortunately, we can't solve every differential equation, so we like to have some tools for estimation. So suppose you were asked to sketch the graph of a solution of this initial value problem. We don't have a formula for the solution, so how could we possibly sketch its graph? Well, we know what the derivative looks like, and we know a point on it. So we know what the solution looks like really close to that point. So we just draw a little picture of our solution really close to that point. And what we can do is pick lots of points and draw lots of little solutions, and that's called a slope or a direction field. There's a pretty picture of one. So, at the point 1, 2, the slope is 3. At the point 0, 1, the slope is 1. Drawing these solution curves in isn't an exact science. You just have to do the best that you can. Notice they drew in curves that are parallel to nearby line segments, and it makes a pattern. So, even though I'm not going to make you draw a slope field, I'm going to go through the steps of sketching this one just to kind of give us an idea of how it would work. So, to help me in my sketching, I'm going to start with some axes. So the differential equation here, example 1, is dy dx is equal to the negative of x over y. So usually I like to think about, where do I have my flat lines? My flat lines meaning, where is the derivative equal to 0? Where does dy dx equal 0? Well, it's a fraction, so it's equal to 0 when the numerator equals 0. So that would be when x equals 0. Well, x equals 0 all on the y-axis. So I'm going to draw a bunch of flat lines all along the y-axis. Now, where would my vertical tangent lines be? Where is dy dx undefined? Undefined. Well, that's when the denominator equals 0. So when y is equal to 0, oh, that's the x-axis. So I'll draw vertical lines all on the x-axis. Now, let's think about quadrant 1. In quadrant 1, I have plus x coordinates and plus y coordinates. So that means if I have the negative of a positive over a positive, I expect all of these slopes to be negative. So dy dx is less than 0. So let's just pick a couple of points and sketch the slope. So at the point 1, 1, my slope is equal to negative 1. At the point 2, 2, my slope is equal to negative 1. All along the identity line, my slope is equal to negative 1. Well, over here in quadrant 3, I have a negative over a negative. So dy dx, again, is going to be negative, and I'm going to have the same slope all along the identity line. If I pick a number where x is bigger than y, since x is on top, I'm going to have a slope that's steeper. So it would be more like that. And if I pick one where y is bigger, it's going to be a little flatter. So let's put in some more in quadrant 2. In quadrant 2, x is negative, y is positive, so my derivative is going to be positive. So I expect positive slopes. If I go along the opposite of the identity line, my slope is always positive 1. Right here, x is equal to negative 1, y is equal to 2. So my slope is going to be positive, something a little bit steeper because x is on top. Actually, x is on top, so it's a little less steep down here where x is equal to 2 and y is equal to 1. It's a little bit steeper, but it's still positive, not negative. So positive. So these, y is always equal to 1, x is going to be on top, so it's going to get steeper and steeper and steeper and steeper as I go along. Steeper, steeper, steeper. Same thing down here. We're positive, so it's positive 1 all along that identity line. If I pick a number here where my y is bigger than my x, then it's going to be steeper. If I pick a number, a point here where my x is less, and you can start to see the pattern there. It's steeper, flatter, flatter, steeper. And it's starting to make a circle, and oh, look at that. There's the pretty picture that I got using Desmos. So you can logic your way through it. If you really had to draw one, you could do it, but I won't expect you to. I would expect you to be able to look at that and pick out that that is indeed the direction field for negative x over y. Now, I printed out this next practice one so I could write on it. Says the direction field for y primed equals the tangent of 1/2 of pi y is shown. Sketch the graphs of the solutions that satisfy the given differential, the given initial conditions. So y of 1 is equal to 0. Y of 0 is equal to 1. If x is equal to 0, y is equal to 1. So that means we're going through this point right here. And I'm going to make this a little smaller, and I'll make that a little bigger so we can see it better. So here, and you just kind of follow the lines. It would look something like that. Again, it's not precise. I don't expect it to be exact. Yours could be slightly different. It does need to kind of follow the lines and hit the initial point. So y of 0 is equal to 0.2. So if x is equal to 0, y is 0.2. So that was 1.2 is about right here. So it's going to go back further that way. Y of 0 is equal to 2. Well, y of 0 equals 2 is a flat line. That means the derivative is equal to 0. 0 is equal to tangent of 1/2 of pi times y. So that means tangent of pi times y is equal to 0. So pi over 2 times y is equal to some constant multiple of pi, equals pi times k. So y is equal to pi k over pi halves 2k. So we expect these flat lines here at every even y value. These are called equilibrium solutions. There's no incentive to change. It's at equilibrium. The derivative is equal to 0. It's not increasing or decreasing. And let's sketch one more. We have y of 1 is equal to 3. So 1 and 3 would be up here somewhere. And it would look something like that. Just following the pattern of the points. Okay. That's the kind of problem you would be expected to do. You would be expected to locate equilibrium solutions where horizontal lines are, and you would be expected to sketch a solution. I printed out the matching so that I could write on it and make it a little bigger so I could see it better. So I'm going to start with A. And the first thing I like to do is figure out where my flat lines or my horizontal tangents are. So I'll take A and set it equal to 0. Y primed is equal to 2 minus y equals 0. Well, if that's true, 2 minus y equals 0, then y is equal to 2. I'm expecting horizontal lines all along the line y equals 2. So I look over here at my slope fields. This one has horizontal lines at 2, and this one has horizontal lines at 2. So I'm going to have to work a little harder for it. So the next thing I notice is that my derivative only has y's in it. So y primed depends only on y. So if I choose a value of y, then my slopes should all be the same. So since it depends only on y, this means that y prime will be the same along any line y equals a. So if I take my ruler and I look at any line y equals, say, 3, I expect all of the slopes to be the same. They're not. Let's try this one. Oh, look at that. Y equals 3, the slopes are all the same. Y equals 1, the slopes are all the same. Now, some more things we could check just to prove to ourselves that 3 is really the right answer. If y is greater than 2, then the slope would be 2 minus y. So y primed would be negative. Oh, look, it is. If y is less than 2, then y primed is going to be a positive thing, because I would have 2 minus something less than 2, so y primed would be positive, and you can see that it is. And we also know that this is an equilibrium solution. And just because vocabulary is so much fun, it's a stable equilibrium because all of the other little slopes are pointing to it. It's as if the slopes want to be there on that line, y equals 2. So, equilibrium, and we know exactly which one this is. This one represents A. So let's do a similar thing and figure out which one represents B. Let's look at 0 equals x times 2 minus y, and we'll figure out where its flat lines are. So x equals 0, which means it has flat lines all along the y-axis. And 2 minus y equals 0, which means along the line y equals 2. Oh, well, let's look at number 1. We have flat lines all along y equals 2, and we have flat lines all along the y-axis. So this is going to be B, and this is going to be slope field number 1. You can also look at your signs of your slope. If we pick a point here, something like the point 1, 1, then I would have 1 times 2 minus 1. I expect a positive slope. If I pick something up here where my x value is going to be, let's see, 1, 3, for example. So my x value is positive, but 2 minus my y value would be negative. I'm going to have a negative slope. Over here, my x values are always negative. If I choose something where 2 is less than, where y is less than 2, I expect a negative slope because I'll have a negative times a positive. And if I choose something where y is bigger than 2, I'll have a negative times a negative, so a positive slope. So there are lots of reasons you can give for choosing a particular slope field, and you'll have to pick a reason when you choose one. At least one reason. And we have an equilibrium solution, but it's not stable because the slopes are pointing away from the equilibrium. Now, let's look at C. Y primed is equal to x plus y minus 1. I want to know where my flat lines are, so in this 0 equal to x plus y minus 1. Well, that's a line. Let's get it in y equals mx plus b form. So y equals, I'll leave y over here, I subtract x and add 1 to the other side. So y equals negative x plus 1. So I have flat lines along the line y equals negative x plus 1. So I expect a flat line on the y-axis at 1. So this is 1, and this is 1. And I expect flat lines all along that line. Oh, look at that. It fits perfectly. So C is this one. And you can check your signs. You could pick a point and plug it in. But if y is greater than negative x plus 1, we expect a positive slope when it's above. If y is less than negative x plus 1, we expect a negative slope right there where it's below. Awesome. Easy enough. Now, we're not going to say the last one has to be number 2 because that's the only one left. We're going to actually look at it. Y primed is equal to sine x sine y. That's equal to 0 if sine of x is equal to 0. So if x is equal to pi times a constant, or if sine of y is equal to 0. So if y is equal to pi times a constant. So that means I'm going to have flat lines all along the x-axis and at pi multiples going up and down. And I'm also going to have flat lines at pi multiples of x values along the y-axis and x values. So, and you can see it kind of follows a sine wave look to it. So this one is D, this one is 2. So the reasons you give: look for where the zeros are, find where your horizontal tangents live. That could be a reason. Pick a point, show that you expect points in this region to be positive or negative, and show why your slope field works. Slope fields are all about drawing pictures of potential solutions. Euler's method is all about getting an estimate for a solution. So the basic idea is Euler's method starts by looking at the direction field and following the little pieces that we draw along a direction field and going from an initial point to a goal point, a point that you would like to get to, solution to an initial value problem. The more little steps you take, or the shorter your little lines that you draw along your slope field, the better your estimate is. So Euler's method depends upon its step size, as we call it, or delta x, or a lot of times they call it h. So you can see your line segment here. It starts, and we did an approximation with step size 0.25. You're drawing a bunch of little tangent lines. Approximate values. So here's our procedure. You want to find y primed is equal to some function, and in the procedure it's of t and y. So you're given that y at 0 is equal to some point A, and you want to find the solution at some future point. So you choose a step that's a positive integer, a delta x, and you take your starting point, you compute the derivative at that point, you multiply that derivative by your step size, that's your x that you're plugging in, and then you add it to the previous y. That tells you how much to move along and gives you your new y. So let's kind of write that down. We have some derivative, y primed is equal to some function, and I'm going to use x and y because that's our favorites. And let me make this smaller. I had it really big to look at that slope field sheet. There we go. So y primed is equal to some function of x and y. You're given an initial condition, y of a is equal to b. So your first y is equal to b. You have a delta x, which is your step size. Your step size. So that's how much you're adjusting your x value. So you first figure out y primed evaluated at AB. So that's the slope of that first little piece on your slope field. You multiply this times your step size. X times y primed at A of B, and let's just call it delta x times f of AB. So that's delta x times that first little slope. You take that and add it to your y1. y1 plus delta x times your slope at that first little point. This is equal to y2, the next value of y. And then you start over again. So your x changes to x plus delta x, and excuse me, that was an a plus delta x, and your y changes to y2, which was b plus delta x times f of AB. So your new y, and you do the whole thing again. So we'll do an example and then it'll start to gel a little more. Use Eulers' method with the step size 0.1 to construct a table of approximate values for the solution of the initial value problem. Now, this one doesn't give you an ending point. So I'm going to go from 0 to 0.5. I'm going to get a sheet of paper to write it on because it'd be too big a mess on my whiteboard. Okay, so y primed is equal to x plus y. Y of 0 is equal to 1, and my step size is 0.1. You can call it h, or you can call it delta x equals 0.1 because my independent variable in this case is x. So I know that my first point is 1, 0. I want to get to my next y value. So my next y value is going to be my first y value plus y primed evaluated at 0 and 1. So y primed evaluated, evaluated at 0, 1 times my delta x is equal to the next y value, so y at 0.1. So the value in x is equal to 0.1. So y1 would be equal to 1 plus the derivative at the point 0, 1 would be 1 times delta x. That's the slope of your tangent line. So 1 plus 0.1 is 1.1. That's my next y value. So I'm going to write down the point. The point would be 0.1 and 1.1. So y2 is equal to 1.1 plus, now I need to compute the derivative at this point. So I'm going to grab my calculator. My y primed is 1.2 times my step size, so times 0.1 equals 0.12 plus my old y, which is 1.22. So now I have the point x increments by its step size. Y is now 1.22. So we're crawling along that slope field. Y3 would be equal to y2. New y is now the old y, plus I need my derivative, and my derivative is x plus y, so 0.2 plus 1.22, 0.2 plus 1.22. There we go. 1.42 times my step size, the slope of the tangent line, times the change in x, so times 0.1 plus 1.22. And I get 1.362. So this is my new point. X is 0.3, y is 1.362. And we can keep going. I said I was going to go until I got to 0.5. So y4 is equal to my next point, y1, y2, y3. This is y4 that we're calculating now. I have y3, 1.362, plus my slope, so 1.362, 1.362 plus 0.3 equals 1.662 times 0.1, 0.1662. I went ahead and multiplied. This was 1.362 times 0.1. Oh, I added 3 to it. It was 1.662 times 0.1 because I did the multiplying. 1.362 plus 0.3, and then I multiplied by 0.1. Okay, and now I add that back to my 1.362, and I accidentally multiplied too many times, so let me just type it in again. 1.362 plus 0.1662 gives me 1.5282, which is my next y, and we could follow along, and we see there is my fourth term, and then my next one would give me the 0.5, the value when x is equal to 0.5, which was my goal. And there's the pretty picture. Now you can see that's kind of tedious. Excel is really good at doing tedious arithmetic. So let's use Excel. So let's see. Here's some pretty pictures that show how much better you get the smaller the step size is. So let's use this practice problem. Actually, let's set this practice problem up instead of doing it like this using a table. Because you are going to have to do one by hand on test day, and I think using a table will help you to set it up. I make a row for x, a column for x, a column for y, a column for y primed, a column for y primed times delta x, and then a column for my new y or next y. And we want to use a step size of 0.2 to estimate y of 0.6, where y of x is the solution to this initial value problem, and y of 0 is equal to 0. So this would be a reasonable test question to expect you to do by hand, because you're starting at 0, 0. Your step size is 0.2, and you only have to do 0.2, 0.4, 0.6, and you'll be done. So this one would not be that challenging to do, and you would be expected to do something no more complex than this on test day by hand. So I'll start filling in my chart. Y primed was equal to cosine of x plus y. So cosine of 0 is equal to 1. 1 times my step size, and again my step size is 0.2, is equal to 0.2. So 0.2 plus 0 is 0.2. So 0.2 comes down, and it's my new y. So now I have 0.2. 0.2 is a point. I need to find my derivative, so y primed is cosine of 0.4, which is a long number. So y primed was 0.92, and I'm only going to write down the first 3 digits, but I'm going to keep them all in there to keep it as precise as possible. And then I multiplied that by my delta x, so times 0.2, which gives me 0.184 plus my old y, which was 0.2. So my new y is about 0.384. I add 4 to it, 0.4 to it. Then what I want is the cosine of x plus y. So I do cosine second answer, and I get 0.708. I multiply that by 0.2, and I get 0.142. I add that to my y, 0.384. And yes, I'm losing some of my accuracy because I'm using these numbers, but I'm keeping as much as I possibly can with my calculator. My new y, oops, I forgot to write down that one, 384. My new y is 0.52. 6, 0.52558898 approximately. This was my goal. I can stop now. So let's see how we did. Oh, I don't have the answers there because it's a practice problem. So we will trust that that's correct. Now it says to repeat part A with step size 1. So what we'll do is we'll do part A with Excel just to make sure we got it right. So I'm going to open up an Excel workbook, and then I'm going to make it bigger so we can all see it. And I'm going to make the columns just like I did on my table. I'll make one for X, one for Y, one for Y primed, which happens to be equal to the cosine of X plus Y. I'll make one for Y primed, and that should be Y primed. Y primed is equal to that. Make that column wider because I want to be able to see the whole thing. Delta X or H or whatever you want to name your step size. So delta X times Y primed. And then old Y plus delta X times Y primed, which is new Y. So I'm going to call it my next Y. First one I had in there was 0, 0 equals cosine of, 0 plus 0. Remember, Excel wants a cell reference. Equals Y primed times delta X, 0.2. Next Y is equal to my old Y plus X times delta X times Y primed. Now, I know that I was supposed to count up 0.2. I needed to count up to 0.6. Just to demo how friendly Excel is. I'll make it do the counting for me. Establish a pattern, move to the corner, drag it, it continues the pattern. So now this one is equal to that one. I already typed all this stuff in. I don't want to type it again. I'll drag it down. And now I have everything filled in that I need. I drag it all the way down, and these are unnecessary, so I delete them, and what I really have is 0.5258 and 52558. I probably wrote something down. Oh, 5258. That's exactly what I have there. So, good enough. Let's do it again with a step size of 0.1, just for practice. Now, I'm going to go ahead and let Excel cover up the whole screen because I like to put some borders around here because borders make it pretty. You also know that Excel is keeping more digits up here, and I like to highlight my final answer. So, let's go back and do it again. We're going to have the exact same headers, so I'm going to copy those and paste them. This time my X's are going to go 0, 0.1. I've created a pattern. I move to the corner, and I ask Excel very nicely to continue my pattern until it gets to 6. My first Y is equal to 0. This is equal to the cosine of X plus Y. Excel-like cell references. Equals delta x, 0.1 times my derivative, equals my old y plus delta x times y primed. Now, my old y, my new y becomes my next y. It's equal to that one. I have to highlight these three, copy them down. I highlight all of them. I can just double click and it fills in the whole thing, but then I don't need these because I only need this answer right here. And you can see it's getting better and better every time. Let's do another example. This is Newton's law of cooling, which you've probably seen before. Get a sheet of paper. Okay, Newton's law of cooling tells us that the rate of change of the temperature of an object is proportional to the difference between its own temperature and the ambient temperature. So let's look at what we have there in the problem. We have a 95-degree cup of coffee is placed in a room that is 20 degrees Celsius. The rate of cooling when T equals 70 degrees Celsius is 1 degree Celsius per minute. So I know my initial temperature. I'm going to let T of little t, capital T of little t, is equal to the temperature of the coffee after t minutes. Because I'm given a temperature or a rate of change in degrees Celsius per minute. So now I have the fact that the ambient temperature or room temperature, and we'll call it A for ambient temperature, is the temperature of the room, which is 20 degrees Celsius. We know our initial temperature of our coffee is 95 degrees Celsius. And according to Newton's law of cooling, the rate of change of the cup of coffee, so D capital T, D little t, is proportional to the difference between its own temperature, so capital T, and 20. I need to know what K is. Well, I happen to know what dt, d little t is when capital T is equal to 70. It's equal to K times 70 minus 20, and it's cooling at a rate of 1 degree per minute, so it's equal to minus 1. So K times 50 is equal to minus 1. So K is equal to minus 1 over 50. So now we have a differential equation. dt is equal to negative 1 over 50 times t minus 20. And I have my initial condition that t at times 0 is equal to 95. So I officially have an IVP, an initial value problem. We want to use Eulers' method with a step size of 2 to determine the temperature of the coffee after 10 minutes. So if I were going to do this by hand, I would have a column for little t, and it would go 0, 2, 4, 6, 8, 10. Then I would have a column for the temperature. I would have a column for the derivative, d primed or dt. Then I would have a column for the derivative times the step size, and we're given a step size of 2. And then I would have a new temperature or next temperature. So I'm going to set that up in Excel for us, and then we'll figure it out using Excel. So I just set up my table. I haven't done any work yet. My initial time is 0. My step size is 2, so I want to count by 2s until I get to 10. And there it is. My initial temperature was 95. That's part of my initial value problem. My differential equation is negative 1 over 50 times, open up a set of parentheses, 95 minus 20 for the first one. This times 2. 2 times the derivative gives me the change in y, so 2, the step size, times the derivative gives me my delta y equals t plus delta t, change in temperature, equals this one. Don't want to type all that stuff in again because I'm way too lazy. And I didn't mean to do all this. I can delete it. I could just have done this right on top of it. But I know I don't need those. But I do know that after 10 minutes, my coffee's down to about 81 degrees. Let's see if we have other questions. Okay, there's the pretty answer. There's where I set up the table. There's where I filled it all in. And yes, I used Excel, except that I put in all of the calculations when I typed it up for you. Okay, another practice problem with Eulers method. We want to use Eulers method with a step size of 0.1 to calculate y of 2, where it's the solution to the following initial value problem, and y of 0 is equal to 1. So I'm counting by 0.1 from 0, let's see, 0 all the way up to 2. I don't want to do that by hand. I'm going to use Excel to do it. So you give it a try, we'll come back, we'll compare answers. How'd you do? Did you get it? So first thing I did was I set up my headers, x, y, y prime times the step size, and then next y. My first initial condition, x was 0, y was 1. Y primed was equal to x cubed minus y cubed. So I used cell references. I multiplied that by 0.1. I added that to y to get my next y. I brought this down to my next y. And then I copied it all, and I ended up with about 1.9. So I wouldn't expect you to do one with 20 steps on the test. I might expect you to do one with 3 steps on the test. That would be reasonable. Try to do the ones on your lab by hand. that'll give you good practice. If you can do those, then you'll be well prepared for test day. You got this.